All right, two of the types of things, quantities that we're going to be dealing with the most in chemistry are mass and volume. You need to be able to convert from volume to mass and mass to volume. Unfortunately for us, if you look at your best friend's butt, the back of your periodic table, will you find a conversion of grams to cubic centimeters? Or maybe liters to grams? No, it's not there. But it needs to be there. But it's not there. That's why one of the most important attributes you can ever deal with in chemistry about a certain substance is its density. Because density is going to relate mass and volume together. So the targets for today are, can you determine the density of solids, liquids using data provided? And can you use the density of a substance to determine mass or volume if I give you all the information you need? Look at these two bricks. One is a brick, one is a styrofoam brick. Notice that the brick weighs more than the styrofoam brick, and yet they have the exact same volume. Why? If you were to look at these guys under the microscope, you would find something very interesting. First of all, a lot of people would say, well, that's real easy because a molecule of brick weighs more than a molecule of styrofoam. And they would be wrong. A styrofoam molecule is about 3 times bigger and heavier than a brick molecule. If that's not the case, then why? Look at it. Raise your hand if you think you've got it. Ryan.
There's more like space in the styrofoam than there is in the brick.
Exactly. Look at that. Look at all the empty space. Yes, these guys are heavier than these guys, but these guys are just more closely packed together. There's more of them in this tiny little volume than they are of the styrofoam. And that's the key thing.
Density. Just like all matter, water has physical properties that can be measured and calculated. To find the mass of water, you need a beaker and a scale. First, find the mass of the empty beaker. Then, fill the beaker up with your desired amount of water. Next, use the scale to find the mass of the filled beaker. To find the mass of just the water, we need to subtract the mass of the empty beaker from the full beaker. Our sample is 100 grams. The volume of water can be measured using a graduated cylinder. Our sample is 100 milliliters. Density is calculated by dividing the mass by the volume. Plug in your measured mass. We measured ours to be 100 grams. Divide that by the measured volume. Our volume was 100 milliliters. Water's density is 1 gram per milliliter. Objects with a density greater than 1 will sink when placed in water. Objects with a density of less than 1 will float when placed in water. If a block has a density of 0.1, it will float because its density is less than 1. Another block with a density of 0.5 will also float because its density is less than 1. Notice that more of the block was below the waterline. Another block with a density of 0.9 is also less dense than water, so it will float. We can see that as density increases, more of the block is below the waterline. Scientists have discovered that the block's density tells exactly where the block will come to rest. If the density is 0.1, then 10% will be below the waterline. To calculate where a block will come to rest, just convert density to a percent. Density also explains why ice floats. If you freeze water, it expands. Let's use the black dots to represent the atoms in water. When you freeze water, no new atoms are added to the water. So because of the expansion, there is more room between the atoms. Compared to the atoms in liquid water, the atoms in the ice are not as tightly packed together, causing the ice to float. So try calculating density for yourself. It's mass divided by volume.
Every substance has its own particular density. And that is really, really important to us. That's why it's not on the back of your periodic table, because it depends on the substance. There will be one density that I will expect you to memorize, and that is the density of water. Quickly, memorize it. 1 gram per milliliter. That's it. 1 gram per milliliter. That's not hard. It's the one density that I'm going to ask you to memorize. The one. Why is that so important? Because if you know the number of milliliters, 50, how many grams do you have to have? 50. What if you know the mass? 100. How many milliliters? 100. Yeah, that's right. So density is so important to us because it has units of grams and milliliters in it, gang. So if I say that density of water is 1 gram per milliliter, then that's like saying 1.0 grams equals 1.00 milliliters. It's an equivalency. And now we can use it in factor labeling. All right? And that's what let's do one example here. There's 4 of these in your homework. This is how you do them. Suppose a student finds a 23.5 milliliter of a certain liquid and weighs it to be 35.062 grams. What is its destiny or density? Well, this one you actually don't need a train track for, because what is density? Mass divided by volume. All right, do we know the mass? Everyone be calculating this. I'm going to call on somebody to give me the answer. And that somebody is Natalie. $1.49 what? Correct, Sig Diggs? Yes? Yes. Is there clothing on that number? Yes? Yes. You are awesome. Good job. You're the first person all day that's not sand. Well, what if we have to determine Natalie's volume? Natalie, first of all, I think we can say is an irregular object. What if she was a regular object, like a cube or a rectangle or whatever? How would you find the volume? Max? And that is?
There's a math formula for each regular object. So for like cube, which one? Yes.
For the volume of anything.
Oh, length times width.
Okay. So if it's an object that you can measure its length, width, and height, then you can find its volume that way. But look at Natalie. I mean, length, width, and height? No. We're not even perfect on either side. So just because you find the dimensions of one side does not mean it mirrors the other. No. We can't. So what method do we use for determining the volume of irregular objects? Water displacement. There you see Natalie and there's a pool with increments. So what do we do first before we allow Natalie to get into her pool? Measure the volume of the water, right? Then we go, Natalie, you can get in. So she dives in. What's going to happen to the water? Okay, she has totally messed up the whole surface of the water, so we're going to have to wait till the water evens out. And then what do we do? Measure the volume. And okay, so we'll have a measurement before she gets in and a measure after she gets in. And what do? Subtract. But Natalie, it's going to take a few minutes for the water to even out, right? And Natalie's probably going to want to try and get up and get some air. So that's why you need a stick, so that you can push her back down if she tries to come back up. Because if she comes back up, she'll ruin the measurement. Well, yeah, but compare what this small stick, the volume of this small stick, to the volume of however much part of her body she gets back out of the pool. Totally mess it up. No, we need the stick to push her back down. Just hold your breath. 2 or 3 minutes, okay? Mercury has a density of 13.6 grams per milliliter. What did they just tell you? That's right. Density is something awesome. It's like something you could put in your back pocket and use it later. You never use density now. It's something to be used later. Density is like having this on your best friend's butt. 13.6 equals 1 milliliter. That's like, if they give you density, that's what they're saying to you. 13.6 grams equals 1 milliliter. Never start with density. What volume of mercury must be taken to obtain 225 grams? So that's where we begin, 225 grams. Train track? What unit are we converting from? Morgan? To? Milliliters. Okay. Look on your best friend's butt and see if there is a conversion of grams to milliliters. Nope, it's not there. So either we're screwed or they gave it to us in the question. Did they? Reach into your back pocket and what do you get out? The density. But the density is like this. We need it to be like this. Can we turn it around? Can we turn it upside down? Oh yeah, it's a conversion factor. And that is the power of density. It allows you to convert from mass to volume and volume to mass. In this case, we needed to convert from mass to volume. Morgan, what's the answer? What? Really? 225 divided by 13.6? Okay. All right. Okay. You're scaring me here. Okay, is that your final answer?
Hold on, wait. I have no idea. Because it's got to be only 3, so it's 16.5. Because there can only be 3 16.
Very good. Now, should you use density to take in consideration? Should you take density into consideration when you're doing your sig-dig calculations? No. Consider densities to be a truth statement. It's like saying 12 inches is equal to a foot. Well, how many sig-digs does 12 have? Actually, it's an infinite number. It's 12.000000. 0.00000 is equal to 1.00000. All right? Consider densities to be an infinite number of sig digs. So really, when you're talking about sig digs, go with the number that you start with, the number that's given to you. That's your measurement. That's the one whose sig digs you should reflect. All right? Questions on this one? A beaker contains 725 milliliters of water. Calculate, two questions. Calculate the volume of water in liquid, in liters. And number two, find the mass of the water. Alec, you want to tackle the first one?
Yeah.
Where do we begin?
It's 0.725.
Oh, thank you. Where do we begin?
Oh, all right. So for 7.5. And then 1 over 1,000.
Who would like to tackle the second question? Simon.
725 grams.
How did you determine that so quickly?
1 milliliter equals 1 gram.
What's the beauty of the density of water? However many grams you have of it, that's how many milliliters. However many milliliters you have of it, that's how many grams. There's only one density that I asked you to memorize, and that was water. And that's why water is so important. So if I give you 50 milliliters of water, and you don't need 50 milliliters, you need to know the grams, are you going to freak out? No. If you have 50 milliliters, you have 50 grams. Here are some densities that are definitely not equal to water. Gold is almost 20 times more dense than water. And mercury is the most dense liquid known to man. It is almost 14 times more dense than water. Last question. Gold has a density of 19.3 grams per milliliter. Mark, what are you going to do with that information? Back pocket. Never start with density. It is your destiny to never start with density. How heavy in grams would a 30 centimeter by 60 centimeter by 10 centimeter block of gold be? So it's 60 centimeters by 30 centimeters by 10 centimeters. Uh-oh. They didn't give us volume. They only gave us length, width, and heights. What are we going to do? What can we do?
Length times width times height.
There we go. All right, Ryan, what is length times width times height?
You calculate it is 18,000.
So that gives us cubic centimeters. Do you have a way of converting cubic centimeters to grams? What? No, that won't really help you. You need something that has grams and cubic centimeters in it. Something. Why don't you go back there to Mark and see what's in his back pocket?
Oh, you can do 19.3.
But wait a second, that says milliliters. It doesn't say cubic centimeters.
Oh, you can convert it.
What is the conversion of milliliters to cubic centimeters?
You don't got one. I don't know.
1 o'clock. Look at your best friend's butt. 1 o'clock.
Which one? There's a lot.
The conversion of cubic world to metric world.
Oh, 1 milliliter equals 1 centimeter.
So it's the same thing.
Yeah.
All right. Who's got the calculation? Katie. Got it? No? No, you're Elizabeth, right? Elizabeth. You have it?
Yeah, I do.
What is it?
3, 4, 7, 4, 0, 0. Oh wait, you need to be. Yeah.
Units?
Grams per cubic centimeter. No, milliliters. Right? Or just grams. I'm so confused.
Have we avoided confusion now? Yeah, that's why it's important to cross out. Okay, is that your final answer? Well, this is like saying around 30, around 60, and around 10. So how many sig digs do each one of those measurements have? So how many sig digs should your final answer be? So what will... Well, if it's... Are you saying that 3 is roughly the same as 347,400? So you need to not use zeros, but not use them as significant digits.
So it needs to be like 3.0.
Okay, what are you going to have to, 347,000. You're going to have to round it up to the nearest 100,000. Do you round up to 400,000 or down to 300,000? Now, how many significant digits do you have? 1. What if I was to put a decimal there?
Then you would have 6.
So that's how you make it into 1. You could have also put it into scientific notation. Be careful with significant digits. Any questions? Morgan? No? Yes? Because round up to 350,000, because how many sig digs would you have then? 2. But you only have 1 here, 1 here.